And we're live. Okay, so today we're going to continue to talk about hierarchical models, and we will continue to talk about how I'm an employee of Columbia University, a co-founder of Stan Group, and therefore subject to this conflict of interest thing. So just to review a little bit from Tuesday, including what I consider to be sort of the fundamental difference between the Bayesian perspective on hierarchical models and the frequentist perspective on hierarchical models. So both sides, so this is the case for a continuous Y, but it's similar if you have a discrete outcome, in which case this equation would apply to the linear predictor. In any event, both Bayesians and frequentists are working off of the same equation for Y. Both are assuming that these U variables, which we talked about last time, are distributed standard normal. Both are, I didn't write this up here, but both are making the assumption that the epsilons are distributed normal with mean 0 and some unknown standard deviation that we're going to estimate. And nevertheless, despite all those similarities, you can get considerable differences in interpretation depending on what part of this equation you consider to be part of the conditional expectation for Y and what part is considered to be the error term. So for Bayesians, the conditional expectation of Y consists of both of these terms here, x times beta, which you can think of as the sort of the linear predictor for the average. So for if the groups here are the 50 states, then this x times beta pertains to the linear prediction for the country as a whole on average. But the other part of the conditional expectation is this plus ZB thing. And this ZB encodes the state-specific deviation from the United States as a whole. So Z is a specially constructed matrix, basically consists of interaction terms between some columns of X and the state level indicators. So it's usually going to have a lot of zeros, some ones in it. It gets multiplied by the corresponding element of B, and that shifts things over if it's the intercept, or it multiplies by a coefficient and then by some number if we have coefficients that vary across states. But in any event, for Bayesians, the conditional expectation consists of both those terms. So the part that comes from the United States as a whole and the state-specific deviation. So all of you live in New York, I presume. Maybe some of you live in New Jersey. You're going to have a state-specific shift to that, and that applies for all of the states that you have data on. And so for Bayesians, the error term, the other part of the decomposition of Y is just these epsilons, which, conditional on the X's and conditional on the Z's are assumed to be independent of each other, and they have mean 0 and some standard deviation sigma. But it's different for frequentists, even though a lot of applied frequentists, as opposed to sort of people who write on frequentism from a methodological perspective, don't really appreciate this distinction very much. So technically speaking, for a frequentist, the part that is the conditional expectation mu is just this part here, x times beta. And the error term consists of the other parts, z times b, where we can write b in the form of this thing here, I Kronecker product L U sigma, plus epsilon. So those two pieces are the error term from a frequentist perspective. So we've got three pieces, x times beta, z times b, and epsilon. So for Bayesians, the first two are part of the conditional expectation, and the last one, epsilon, is the error term. For frequentists, it's the other way around. The first piece, x times beta, is the conditional expectation, and the last two pieces, ZB and epsilon are part of the error term. So in this way of thinking about it from a frequentist perspective, you know, x times b, which still represents sort of the linear predictor for the United States as a whole, is the conditional expectation. And insofar as these coefficients in New York, New Jersey, Kansas, whatever, differ from that, that's considered to be error for the overall US model. So there's sort of an overall US model, and then there's a New York specific error to that, such that everyone within the same state, such as New York, has some commonalities to them that make them sort of collectively deviate from the United States as a whole, in addition to individually deviating from the parameters in New York. And the reason why frequentists do this is because anything that's considered part of the error term, frequentists allow themselves to make distributional assumptions for the pieces of that. And so that's why frequentists get to assume that these U's are distributed standard normal. For a Bayesian, you put a prior that the U's are standard normal. For frequentists, technically this is an assumption rather than a belief. So we got through all that. And so this way of cutting things up from a frequentist perspective, beta is a parameter. Some other things are parameters, but B is not a parameter. And U is not a parameter. Because in order to be a parameter from the frequentist perspective, and consequently only parameters are estimated. So if B is not a parameter, it's not estimated, and that's because it's not fixed in repeated sampling. And that's why frequentists need a special term for the B's, which they call random effects, as opposed to the betas, which they call fixed effects. And so from a Bayesian perspective, you don't really need to distinguish. You don't need a special word to distinguish, you know, betas from B's. They're all unknowns. You have beliefs about all of them. You're going to update your beliefs about all of them, conditional on the data, etc. You don't really need to distinguish between them. For frequentists, it's essential to say what are the parameters or what is fixed in repeated sampling, in which case you can construct an estimator for it, and what is not fixed in repeated sampling. Consequently, you're not estimating it, and that is the B's or the U's, whatever, are considered to be or called random effects to distinguish them from fixed parameters that are going to be estimated. And the reason why they're called random effects is, from a frequentist perspective, the justification for specifying a hierarchical model like this for a data generating process is really tied to this idea of, you know, cluster sampling or some sort of two-stage sampling that, you know, like I said last time, often comes up in education research, where you propose a study. You know, I'm going to sample 100 schools from the population of schools in the United States. And then within each of those schools, I'm going to go to the schools and I'm going to sample, you know, 30 students from that school. And then I'm going to give those 30 students, you know, a test or a survey or something like that. But everything about, you know, justifications for frequentist estimators relies on this idea. Well, how would it perform if we were to repeat this research design over and over and over and over and over again? And if you were to repeat the research design that I just got through describing over and over and over again, where you take a random sample of 100 schools and then within each school take a sample of 30 students so that you have a total sample size of 3,000. If you were to repeat that whole thing again, when you did it the second time, you would take a different collection of 100 schools that you would go to and then take a sample of 30 students within this. So the identities of the school are changing every time you do the study. And so which schools are or are not in your sample from the population is random under that kind of a research design. Now, if you had a different research design where you say, okay, I'm going to select schools once, 100 schools, and then I'm going to, go in repeatedly and take a sample of 30 schools, analyze the data, then go back the second time I do the study to the same schools that I did the first time, take a new sample of 30 students from each and repeat that over and over again. So I was doing it with different students, but the same schools every time. In that case, the schools would not be random. You fix them at the outset and you're just sampling students from within those schools. In that case, the appropriate research design would be to consider those school-specific parameters part of the X rather than part of, or the school-specific variables to be part of the X rather than part of the Z. So from a frequentist perspective, you really have to be explicit as to what sort of research design you're imagining repeating over and over and over again. Are the schools changing, or are the schools remaining the same and only the students change? But applied frequentists in particular are usually not really explicit about what research design they're imagining being repeated over and over and over again, because in point of fact, these research designs are not being repeated over and over and over again. They're extraordinarily expensive to do, something like that for the United States as a whole, and they're, only going to be done once or only once every, 5 years, and in that 5 years, the population of schools changes and, all sorts of other things. So this is entirely a hypothetical, imaginary thing, but this hypothetical, imaginary, seemingly not very interesting thing is how all frequentist estimators are justified and how you have to interpret things like standard errors, p-values, t-tests, confidence intervals. Those all pertain to the distribution of the estimator when you repeat the research design over and over and over again. But most applied frequentists don't really drink the frequentist Kool-Aid. They just, want to get numbers and like publish them or report them to their boss. They're not really invested in this idea that we should evaluate estimators based on their long-term performance over the same population. And so what you'll see in the literature is people really stretching the definition as to what's considered to be a random sample of groups from the population. And so they'll do things like say, I put a random effect for gender, even though, from the purpose of like surveys, there's never been a survey that had anything other than 2 genders in it. And each time you do the study, you get both men and women. So it's not like there's more than, genders that you could have taken a random sample from and you chose to only, take 2 genders. Or they'll put a random, some sort of effect thing for the race categories. Now, there's, different ways to define the race categories, but most of them do like the census definition, which has also changed over time. But there tends to be about 5 or 6 races that are considered by the census. And in your, census data, you have people from all those. So it's not really the case that you took a random sample of races from the population of races in the United States. You have all of them. Or, they'll put in a random effect for the state residence variable. And for most of the past, 100 years, there have been exactly 50 states, and you have people from all of those states. So it's not like the research designs that were sort of intended for this frequentist estimation of hierarchical models, where the number of schools that you have in your sample is small relative to the number of schools in the population. Nobody's taking like a sample of 5 states out of the population of 50 states and just, doing some further study within those 5 states. They're not never, but almost never, particularly if you're working with census data, in which case it's easier to just download the whole thing and analyze people from all 50 states than it would be to then take a sample of the 5 states and just ignore all the information that has already been given to you on the other 45 states. But the reason why frequentists do this is they've been told like that's what you're supposed to do. And it's also empirically true that the estimation tends to work better if you are supplying, you know, reasonable assumptions such as that these U's are standard normal. And so basically what's happening is these frequentist estimation of hierarchical models gets you something a lot closer to the posterior mode if you were to do it the full Bayesian way. And I've said all kinds of snarky things about the posterior mode over the course of this semester, but it's still better than the mode of the likelihood. The posterior mode is closer to the posterior mean, the posterior mean, median, etc., than the mode of the likelihood. You know, if you were to do without making, you know, any distributional assumptions about these random pieces. Now, plain maximum likelihood without making any assumption about the U's does not work well, because one of the assumptions of maximum likelihood is that the sample size goes to infinity and the number of parameters to estimate that are fixed remains the same. And you know that is fine for simple models. But if you think about this hypothetical research design and you imagine, okay, what if the number of observations goes to infinity? Does the number of observations in the like students within schools design go to infinity because you increase the number of schools in your sample to infinity? Or do you fix the number of schools in your sample to be like 100 and take a larger and larger number of students from within those schools? In the first scenario, where you get more and more observations by taking in more and more schools and sampling 30 students from within each school, maximum likelihood is not a consistent estimator for those school-specific deviations, and that's why they have to be considered part of the error term and integrated out in order to estimate consistently the betas. If, however, you fix the number of schools to be, you know, 100 and, you know, kept those the same, but took a larger and larger number of students from those schools, then you could consistently estimate school-specific parameters, but you would need to consider those school-specific parameters to be fixed. And so there's a lot of kind of subtle distinctions when you think about this from a frequentist perspective, subtle distinctions that are glossed over in the empirical literature that's applying SAS-Proc mixed or, you know, Elmer or Stata's XT, whatever, to estimate these models. They're all pretty much using the same frequentist algorithms, but there's a lot of confusion because there's not a very strong appreciation of, you know, these subtle distinctions, and you get a lot of questions like, why are there no confidence intervals for my estimates of the B's? And that's because you didn't estimate the B's, because the B's are not parameters. Only parameters can be estimated. The B's can be predicted by decomposing the residuals, but you really just have this point prediction because, you know, there's not really an estimator for those B's because you don't have the same schools as you do repeated samples. From a Bayesian perspective, all this is a lot simpler. You're not worried about, well, what happens if I were to repeat this research design over and over and over again? You just have the data that you have now. Your beliefs about the parameters are conditional on that data only. You update your beliefs about beta, about B, about sigma, all those things with the data that you have, and then you summarize your posterior distribution. The coding and the estimation and all the stuff under the hood to do this from a Bayesian perspective is a lot harder, but it's already been implemented in RStanArm and BRMS, which we're going to learn next week. So from the perspective of an applied user, it's not really harder to use like the version in RStanArm than it would be to use the version in the LME4 package. Doing it in RStanArm does take longer in relative terms because you're trying to do something more ambitious. You're sampling from this very, very large dimensional space rather than trying to find a single point that's the mode of the penalized likelihood. But you know, most of the things that we're doing in social science don't really have a time deadline that you have to finish by. And so if it takes a little bit longer, it takes a little bit longer. Questions about that?
So, so the strategy of sampling, like if you fix the school versus vary the school, if you look at schools in the fixed effect or more variables in the fixed effect, the likelihood would better estimate the theta.
Well, if you only have a small number of students within each one of those fixed schools, you're going to get terrible estimates and finite samples. But if you fix the number of schools and take an infinite number of students within those fixed schools, then yes, you can estimate the school-specific parameters consistently. But again, this is all just like an imagination thing. Nobody has the money to take an infinite number of students from schools and give them like a test. So, but you do, or you should, if you're going to do this from a frequentist way, commit to what imaginary repeated research design you're thinking about, because that governs what estimator you should choose and how you should interpret the estimates and so forth. Other questions? Okay, so we got to this tadpole example last time, but I think we only saw like this much of it. This is a data set called reed frogs in Richard McElderry's package. We're going to make a tank variable, one for each observation, and call that a factor. When we do binomial likelihood as opposed to Bernoulli likelihood, you need to specify the outcome variable as a matrix with 2 columns. The first is the count of the number of survivors. The second is the count of the number of tadpoles who die. So first column is successes, second column is failures. In this case, we're estimating a simple model that's going to, well, relatively simple model. There's this overall intercept for tadpoles as a whole. And then there is a tank-specific deviation from that overall intercept. And we have one of those for each of the 48 tanks. The prior on those tank-specific deviations is normal with an expectation of 0. So we're interpreting this as deviation from the average environment of a tadpole. But there's an unknown standard deviation as to how much these tank-specific deviations differ from one tank to the next. So there's also a variance or a standard deviation in terms of how much the tanks vary in their intercepts. So that's why this comes out with 50 parameters being estimated. We give it the data set, we specify our family. So by default, this is Gaussian, and that's one of the common mistakes to make, is to forget to specify that family, in which case you're using an inappropriate likelihood for your data. But in this case, we specify binomial with the logistic link function. It comes back pretty quickly. 4,000 draws from this 50-dimensional posterior distribution. And if you call the varchor function, which is something that originates in the LME4 package, so in addition to basically copying the syntax that the LME4 people have popularized for specifying these hierarchical models, when it makes sense, and sometimes even when it doesn't make sense, the RScan arm will also provide methods for the post-estimation functions in the LME4 package, so they more or less behave the same way. And so in this case, we're asking for the variance covariance matrix of the tank-specific parameters. In this case, there's only one, so it's a 1-by-1 variance matrix, otherwise known as a scalar, and that standard deviation, at least its mean, is estimated to be 1.63. So the tank-specific deviations have, you know, a posterior expectation of 1.63 standard deviations.
What are the starting values of the hyperparameters, or are there any ones in this?
They're chosen randomly.
Okay.
Doesn't matter too much. Shouldn't matter too much. So I'm not sure if I said this on Tuesday, but really what makes the LME4 package great and was what has made it so popular over the past many years is the syntax for concisely specifying these hierarchical models in a flexible way. And it's the same, although in my opinion, less true for SAS, product mixed, and Stata, and other things that have this hierarchical model frequentist estimator. But this nice syntax is not something that's tied to the frequentist way of looking at things or the frequentist way of estimating things. So we can, borrow or steal, depending on your perspective, that syntax and use it to estimate, these models from a Bayesian perspective, which would actually be a lot more intuitive from a lot of people's perspective, and is. And so, people are pretty happy with this. And so, I would say, LME4 isn't successful because people love frequentist estimators. And in some ways, it tends not to be so successful because it's a frequentist estimator. But the reason why it's well-liked and popular is because it makes things convenient. But we can make things convenient from a Bayesian perspective as well. And in a simple model like this, the GLME function in the LME4 package works pretty much fine, I think. But you might as well do the Bayesian thing in order to interpret everything in terms of your uncertainty about the estimates in terms of probability. So if you just print out the object that's returned by this, you get a printout that is similar-ish to the printout that you would get from LME4. So it's estimating the overall alpha parameter, the sort of tadpole-specific log odds of survival, is having a posterior median of 1.4 and a posterior standard deviation of 0.3, or at least those rounded to 1 decimal point. Again, we see a standard deviation of about 1.6 on the differences in the deviation from one tank to the next. Our stan arm always puts also the mean of the posterior predictive distribution. This is a good way to check that your model's doing something reasonable. It's saying, for this data set overall, it's predicting 16.3 tadpoles to survive in each tank overall. Although in each tank, there's, a deviation from that. So this is the sort of output that you get from Stan Glimmer, similar to the output you would get from LME4. But remember, LME4 only has point estimates behind it. I mean, they also have standard errors for the betas, but they essentially just have points, or single points. Whereas with Stan Glimmer, you actually have this 4,000 by 50 matrix underlying it. And what you see on this with these medians and stuff is the median of those 4,000 things for the corresponding parameter. But you can actually access all 4,000 of those draws to summarize your uncertainty about stuff in a straightforward fashion, inclusive of your uncertainty about the B's, which you don't even get if you do a frequentist estimator. And the standard errors of the beta hats with frequentist estimators are known to be too small because they don't propagate the uncertainty about the B's to the estimates. So other things that you can do, so this is something that's aggravating, but we decided to do it in order to keep as much consistency as possible in with the LME4 package. You can call the fixf function, and you will get estimates of the so-called fixed parameters, which in this case is the sort of, for tadpoles as a whole, log odds of survival. Now, I just got through saying, from a Bayesian perspective, there's no reason to distinguish between fixed parameters and random effects because these are all unknowns from a Bayesian perspective. You're going to update your beliefs about all of them. But because, the LME4 and its syntax and its functions and whatnot were already out there, we decided to adopt the same conventions, even though they don't make as much sense from a Bayesian perspective. So another one is the RANF function, which is going to return point estimates for how much each of the 48 tanks deviate in their log odds from the overall estimate for tadpoles as a whole. That is a list because you could have more than one group specific parameter, or it's a parameter from a Bayesian perspective. So that if that was the case, then this list would have more than one element, but in this case, it just has the tank specific deviations. And anyway, there's 48 of those. Another thing you can do is called the COEF function, which in the case of Stan Glimmer model also returns a list. And what COEF does is it adds the overall estimate for the log odds of survival of tadpoles as a whole to the tank specific deviation to that log odds. So for each tank, you get this prediction for what's the log odds or survival. Here I've summarized the first 6 of them, and you can see that all of these are equivalent. So COEF is basically equivalent to the sum of fixF and RANF for each of the group variables that you're allowing the parameters to deviate on. This is the overall log odds of survival for tadpoles as a whole. Then for each tank, of which there's 48, you shift that a little bit. And then the sum of those two things tells you the log odds for the first tank or the second tank, at the medians. All of which you could obtain yourself from, adding columns of the 4000 by 50 matrix together. But we have convenience functions to do that for you. But that's not an excuse to ignore your uncertainty about these things, which can be considerable if you don't have that many tadpoles in a tank. So pretty much everything that you can do with the models we started with before spring break, you can also do with these hierarchical models, including call pp_check function, giving it the result of the thing that was output by rstan_arm, and a character string saying what function you want the posterior predictive distribution to be looking at. So here we have a solid blue line, which represents the density curve for the proportion of survivors in the data set. So this is the proportion of survivals in the actual Y data. And each of these sort of light blue lines, maybe there's 20 of them or something, is a draw from the posterior predictive distribution as to what the model thinks would be the marginal distribution of survival for these tadpoles, taking into account all the tank specific shifts to the intercept. And so unlike the model we were working with before spring break, this one, the posterior predictive distribution, does a decent job of capturing the bimodality in the raw data. So this is not perfect, but it's not bad. It might not exactly catch, all of this, but it seems to be doing a pretty good job, even though it's a pretty simple model. And so we could investigate this, even more. Maybe we do need to make this model a little bit more complicated, but it's not a bad start according to this posterior predictive check. But this is another one of the advantages of doing things from a Bayesian perspective, is that you get, multiple draws from the posterior predictive distribution that you can plot or summarize to characterize your uncertainty about things. In which case you have a better ability to say, are the thin gray lines close or far from the dark blue line, which represents the marginal distribution of the data when you have, you know, a bunch of them to overlay. If you just had like a single line representing point estimates, it would be hard for you to say like, are these two lines sufficiently similar to each other or not? In addition, the nonlinear transformation of a logit model, you know, messes things up. You can't just take your point estimates, do a nonlinear transformation of them, and say, okay, this is my posterior expectation of the probability of survival. It doesn't work that way with nonlinear functions, which is why you have to put the whole posterior distribution into the nonlinear function and then summarize it on the other side.
So you have to do each individual point.
Yeah. So this is only 20 out of 4,000, but we could have put all 4,000 on here, and that's the right way to do it. The wrong way to do it, even though it's a common way to do it, is to just go back, like take these point estimates, you know, 1.4 or, you know, whatever the shift was, get something like this, 3.01, and then, okay, that's log odds. I'm going to convert that to probability by putting it into the logistic CDF. You get out a number. That number is not an expectation. It's not a median. It's not even a mode. It's not anything. It's just a number. Because, you know, nonlinear functions have, you know, different effects on these summary statistics like mean and standard deviation and median and all that. So the right thing to do, which is what the pp_check function does, is take a bunch of draws from the parameters, stick them into the link function, transform it out. Now you get a distribution for these probabilities, and you can summarize that distribution in a plot or numerically. So if you're going to reduce stuff to like a single number, like a mean or a median or something like that, always do that at the very last step. Then it's fine, you know, for what it is. You can legitimately say, this is a posterior expectation. This is a posterior mean. This is a posterior variance. If you reduce things to a number and then like do more steps, more functions, more transformations, what you get out at the end is wrong. It's not an expectation. It's not a mean. It's not a variance. It's just a sort of unidentified number. So don't do that. But RStanArm will tend to do the right thing for you.
Is this why? Wouldn't the y be the actual survival thing?
So this is the proportions of survivals from each tank. So y is a little bit of a misnomer, but it's empirical. It's from the data. This is what we're trying to model. Nigel?
But isn't, for multi-level models, isn't the y, shouldn't it deviate from the y rep, because that you're trying to pull stuff together and there's pulling, that it should actually be further away. So we just look at the shape rather than the deviation.
Yeah, I mean, it shouldn't be too far away. It shouldn't be systematically far away. But for each point along the line, you know, it's going to differ somewhat. Like right here at like 0.62 or something like that, it seems like all the deviations kind of tend to be on one side. So that's not great. But, you know, for most of it, the solid blue line is kind of more or less splitting the middle of what the model distribution implies for the same quantity. So this isn't bad. Could be better, but not bad. And we know that it's not perfect. And we know that it's not horrible, which is not something we would know if we didn't use Bayesian stuff. Question? Okay. So there was a question last time, well, what if you do a more complicated model where you don't just have intercepts that vary across tanks, but you have multiple parameters, let's say K parameters that are group specific? How would you specify a prior on these hyperparameters? And the reason why this is difficult is because there's a covariance matrix, big sigma, that you have to express your beliefs about, and many people find that to be extraordinarily difficult. If you go back to the not so distant in time literature, you'll see a lot of people before there was Stan using Wishart priors, or even worse, inverse Wishart priors for covariance matrices such as sigma. And the reason why they do that is because if you make that particular prior assumption, then there's going to be conjugacy between the priors and the hyperpriors and the likelihood. And you can derive a Gibbs sampler, which is what people who wanted to do Bayesian stuff were using before Stan came along. However, Gibbs samplers, unless you have like a lot of data within each group, can be very poor, very inefficient in terms of their ability to estimate the parameters with a finite number of draws in the posterior distribution. You almost literally have to take an infinite number of draws from the posterior distribution in order for those averages to converge, like Monte Carlo integration claims they'll converge, to the true posterior expectations. And this is confusing because no one really understands the properties of inverse Wishart distribution to begin with. But it's also, I think, harmful in the sense that the Gibbs sampling, even though it was the only way you could do this model from a Bayesian perspective for a long, long time, forces you to think in terms of very restricted choices for your priors. So instead of saying, well, what do I believe before I see the data about this covariance matrix, you ask yourself the question, well, how can I express what I believe about this covariance matrix in terms of an inverse Wishart distribution? I don't even understand what the inverse Wishart distribution is to begin with. So how could I possibly express my beliefs about a covariance matrix in terms of that? However, if you ask someone to express their beliefs about a covariance matrix, particularly one that's greater than 2 by 2, they will usually say something that is contradictory to the definition of a covariance matrix. And one of the essential characteristics of a covariance matrix is that it needs to be positive definite. We talked a little bit about this in the week on matrix algebra. I don't think we dwelled on it at the time. But basically, a positive definite matrix is sort of the analog of a positive number if you're just talking about a scalar number. And so if we had like a 1 by 1 covariance matrix, which is really just a variance, we would require that variance to be a positive number. There's no such thing as negative variance. When we extend the matrix to be not 1 by 1, but k by k, where k is greater than 1, we still have this requirement that the matrix be positive definite as a whole, but that does not really simplify into, an obvious, if the elements of the matrix are this, then it's positive definite. If the elements of the matrix are something else, then it's not positive definite. So that's a very difficult thing for people to wrap their heads around. And if you ask somebody like, what's your prior expectation of this matrix, they'll probably like look at you like you're crazy. But even if they give you some prior expectation, that prior expectation probably won't be positive definite, in which case it's an illegal covariance matrix that they're ostensibly saying this is what I expect it to be. And so all of this is easier with Stan because you're free to do what makes sense insofar as you can make sense of this. And one of the things that's proven to be very successful with Stan is to stop thinking about covariance matrices as primitive parameters. Instead, decompose them into standard deviations and correlations. Correlations are easier to think about because they're restricted to be between -1 and 1, and they're unit free. And you can think about sort of separately the standard deviations. So you might have some more reasonable intuition as to this standard deviation should be large, this should be small. Use like some other distribution for those standard deviations, and then focus on, well, what would be a prior for a correlation matrix rather than what would be a prior for a covariance matrix. Now, once you start talking about a correlation matrix, because the diagonal elements are fixed to 1, then the whole Gibbs sampling thing doesn't work anymore. And that's why they didn't do it for like 20, 25 years. But with Stan, there actually is a correlation matrix type. And so if we let lambda be a correlation matrix, multiply on both sides by a diagonal matrix delta, where the diagonal elements of delta correspond to the standard deviations, then we have a deterministic relationship. Sigma is equal to delta lambda delta. And we can say, okay, what's your prior on the diagonal elements of delta? What's your prior on the correlation matrix lambda? The thing about covariance matrix that one makes them difficult to understand and two makes them difficult to do with MCMC is covariance combines together correlation and variance in the same number. So if I say like, what's the covariance between two people, the units of that are sort of, you know, scaled up by the respective standard deviation. So covariance equal correlation times standard deviation of the first thing times standard deviation of the second thing. And so if you think about covariance, you're sort of thinking about those three things mushed together. Whereas if you do this sort of separation thing in Stan, you can think about the correlations in isolation with the standard deviations. And it's always good to break things down to simpler parts. Okay, so we've broken sigma down to delta, lambda, and delta. And so things have gotten a little bit simpler. And if breaking things into simpler parts tends to make things easier, let's not stop there. Let's decompose again. So the squared elements of delta, which are the variances that we're trying to estimate here, let's decompose that into tau times pi k. So in this decomposition, tau would be considered the trace of the matrix. The trace of the matrix is the sum of its diagonal elements. And these pi's collectively constitute a simplex. So they're positive numbers between 0 and 1 that add up to 1. And so if all of these pi's, they add up to 1, and we multiply them by tau, then the sum of the squared diagonal elements of delta is the trace of sigma. So we've separated big sigma into correlations and variances. We're going to separate the variance into a trace, which is the sum of all the variances, and the proportion of that trace that is attributable to the kth diagonal element, which is the kth variance. So why might we do that? Well, one reason why we do that is because we have a good prior already that we know for a simplex vector, that being the Dirichlet distribution. And we know how to make the Dirichlet distribution be a uninformative prior by setting all the hyperparameter values equal to 1. So in that case, all simplex vectors of size k are equally likely under our prior. And that's something that a lot of people really like, because they don't usually have strong prior beliefs about any of this stuff, particularly pertaining to variances or covariance matrices or anything like that. So if you give somebody the opportunity to say, okay, I have a uniform prior over pi among the space of simplex vectors, that is like a really good default that most people don't even want to change. So we've broken it down now into tau and pi. So we have the trace, and we have a simplex, and we know a prior for a simplex. So if we set that trace equal to gamma squared times k, k we know it's a constant, it's the dimension of the covariance matrix. So now we might say, okay, well, what's your prior on gamma? And gamma is a scale parameter, and we've already learned a pretty good prior for scale parameters. That's the Jeffreys prior. That's the only prior that conveys the information that the units that the variables are measured in don't contain any substantive information. So you could change everything from dollars to euros. It would scale up gamma, but it wouldn't change any of the other parameters. So if your units are arbitrary, which is most often the case in the social sciences, it's good to choose a prior that basically conveys the information that the units of the variables are arbitrary. So we've got a good prior for pi. We've got a good prior for gamma. We've got equalities that relate, gamma to tau, tau to delta, delta and lambda to sigma. So we can build up this covariance matrix from the parts. So the only thing that's remaining is what is our prior for big lambda, the correlation matrix. And that we get to on the next slide. And so there is a easy and a good prior for a correlation matrix that the Stan manual and whatnot calls the LKJ prior. This was something that was first pointed out in 2009, which was actually before Stan came into existence, by 3 co-authors whose names are Lewandowski, Kuro, Fishka, and Joe. Except me and Bob Carpenter, when we wrote this, could never remember how to spell Lewandowski or Kuro Fishka. So we just abbreviated this to LKJ, which are the 3 authors of the paper who proposed this distribution for correlation matrix, whose PDF takes this form. It involves the determinant of the correlation matrix and a shape parameter, which we'll call eta. And eta acts like the shape parameter for a beta distribution if the 2 shape parameters of the beta distribution are constrained to be equal to each other. So if eta is equal to 1, you're raising this determinant to the power of 0. Anything raised to the power of 0 is 1, in which case the PDF is constant over the space of positive definite correlation matrices of order k, which is the default, and what a lot of people just stick with that because they really don't have any information about, prior information about a correlation matrix. And even if they do, that information is probably wrong because it would contradict the positive definiteness requirement on correlation matrices. However, if you choose the eta parameter to be greater than 1, then the mode of this distribution for correlation matrices is at the identity matrix. So under this prior, if eta is greater than 1, the identity matrix is the most likely correlation matrix under this prior. And so sometimes you'll see people put in values of eta that are higher than 1. If you put in eta that goes like closer and closer to infinity, the distribution gets more and more concentrated on the identity matrix, such that if you let eta go to infinity, the only correlation matrix that has positive density is the identity matrix, which is basically to enforce that all of these things that you're modeling are uncorrelated with each other. Now, you don't want to usually make eta to be too big. But for a lot of things, you probably, particularly if this is like for error terms or something like that, you don't think that there's going to be that many big correlations. Like most of the correlations are going to be kind of small, maybe a little bit positive, maybe a little bit negative, but something kind of close to the identity matrix, even though not exactly the identity matrix. If you make eta less than 1, then the identity matrix is the least likely correlation matrix. There's a trough in the density at the identity matrix, which is just a stupid thing to believe in most cases. So you really want to take eta to be 1 or maybe a little bit bigger for most purposes in the social sciences. What we actually do in practice is decompose lambda one more time into its Cholesky factors, and we can work out what is the PDF of a Cholesky factor of a correlation matrix by using the absolute value of the determinant. You don't need to worry about that too much. All of this is already built into Stan. So just to recap, basically what we tend to do in Stan, because we have the freedom to do so, because we're not required to derive full conditional distributions or anything like that, like we would if we had to do a Gibbs sampler, is to keep decomposing things into smaller and smaller parts until we get comfortable with a prior on some of those parts. And just keep doing that until you get comfortable with the prior, and then, you know, build up the thing that you were not comfortable specifying a prior on. So just to repeat the steps that we did, we're going to decompose a covariance matrix, which is hard to understand, hard to put a prior on, into variances and a correlation matrix. We're going to decompose the variances into a proportion pi of the trace, where the trace is the sum of the variances over the k diagonal elements. So decompose sigma into variances and correlation matrix, decompose variances into proportion of trace, decompose trace into k times a scale parameter, and we're comfortable putting a prior on a scale parameter because in almost, you know, all cases, a Jeffreys prior for a scalar scale parameter is a reasonable thing to do. It basically says the units of this are arbitrary. Okay, so we're comfortable with the prior on gamma. We're comfortable with the prior on pi because it's a simplex vector, and pretty much the basic prior distribution for a simplex vector we've already learned. That's the Dirichlet, and we know how to do an uninformative prior on a simplex by making all the shape parameters equal to 1. So all simplex vectors for pi are equally likely before we see the data. Okay, we're comfortable with that. That only leaves what's the prior on the correlation matrix lambda. There is a prior, it's programmed into Stan for that, called LKJ. If we want, we can set eta equal to 1, in which case the density over correlation matrices is constant for all positive definite k by k correlation matrices. Or if we want to get a little adventurous, we can specify eta to be a number positive or more than 1, in which case this density has a mode, and the mode is the identity matrix. So we're basically saying the most likely correlation matrix is the identity matrix. And insofar as we choose eta to be greater than 1, we're saying we're sort of more and more sure about this correlation matrix being closer to the identity matrix. And those, you know, things together, you know, probably anybody could get behind. And they imply some prior distribution for sigma, but it doesn't have a name. It's just the union of the priors, independent priors, on all of these individual pieces. And the priors on the individual pieces, you know, you can get comfortable with. As opposed to saying, okay, I have an inverse Wishart for sigma, and I don't even know what that means. And I do not know what that means. Nobody knows what that means. Inverse Wishart distribution is very difficult to understand, and it tends to produce poor results in Stan anyway. So, no particular reason to use it. Questions about this?
So delta k is the individual element of the kth variance of the trace?
Yes. So the diagonal elements of delta are standard deviations. Their squares are variances. And we're going to decompose the variance into a trace, which is the sum of all variances, and some number between 0 and 1, which is a proportion. So if you're the first element of like a 50 by 50 covariance matrix that we have here, it would be the first element of pi multiplied by the trace. That is the first variance. And you could do it for the second variance and for everybody. And that's because pi is a simplex vector. All the elements are between 0 and 1, and they sum up to exactly 1. So we're just kind of scaling a simplex vector by a trace.
Just to follow up, why your square gamma?
Square gamma in order to interpret gamma as a scale parameter. And a scale parameter, we know how to put a Jeffreys prior on. So yeah, you could put a prior on gamma squared rather than gamma, but gamma squared isn't a scale parameter. So that makes it a little bit harder to choose what you might want to do with it. Jeffreys prior for a scale parameter is pretty standard.
So when we learn them on these pi k's, they change.
Oh yeah, you update your beliefs about
So
those.
the interpretation there is the proportion of variance coming from the kth parameter or something?
Yeah. You can get a posterior distribution on all that.
So you didn't give us a chapter for the next version of Gelman and Hill on hierarchy models?
No, we did not. It's not exactly what you would call written yet.
Because I was looking at the previous, and so when you're mentioning the literature, is that what you're referring to? Because
Yeah, the first version of Gelman and Hill was written in the inverse Wishart era, unfortunately. So that was published like 2006, 2007, and the LKJ thing came out in 2009. And Andrew learned what it meant like last week. So there's another example in McElreath involving chimpanzees and some experiment that someone ran on them. And the chimpanzee had to choose whether to pull the lever on the left or the lever on the right. And they got like food or something like that. But it was, supposed to test like how cooperative a group of chimpanzees are. And so this is not exactly the example in McElreath, but this is something you could do with scan glimmer. So we have an outcome. Do they pull the left lever or the right lever? There's some experimental condition and something about the pro-socialness of the chimpanzee. So these are going to be part of our X matrix. And then there's some grouping variable called actor, which I honestly don't remember exactly what that means. But we're saying, we want the intercept and the coefficient on all these things to vary from like one group of chimpanzees to the next. And also we have an interaction term here, which is, McElreath had that too. So in this case, when we estimate the model, and because we have more than one predictor here, it's good to use QR equal true if you don't want to specify an informative prior on the betas. This is a Bernoulli model. So it comes out, this is a 4,000 by 42 thing. And now, instead of having this 1-by-1 covariance matrix like we had with the tanks and the tadpoles, now we have a 4-by-4 that, 4-by-4. So there's posterior correlations and posterior standard deviations whose means are listed here. So what this tells you, negative 0.230, your posterior beliefs in expectation is that the deviation in the condition variable by group of chimpanzees is correlated negative 0.23 with the group of chimpanzees deviation in this pro-social variable. So this is your posterior beliefs about these correlations when your prior belief about the correlations and the pi's and the gamma and the tau and all that was what I described on the previous two slides. So this, you can change it, but if you don't specify, this is just going to use the default prior on or prior construction on these covariance matrices, and the prior default does this multiple decomposition scheme, and it sets eta equal to 1 by default and all the a's equal to 1 by default and does a Jeffreys prior and stuff like that. So the prior was, what I just talked about, and it tends to work pretty well, and you get to update your beliefs about the standard deviations and the correlations and all that. Okay, so this is an example where the coefficients and the intercept vary by group. And so we have like a 4-by-4 rather than a 1-by-1. Questions?
What is the delta to improve?
So the squares of the standard deviations, the standard deviations go on the diagonal elements of delta. So those are standard deviations. Their squares are variances. So if you squared those, you would get posterior variances in the first column here. So standard deviations over here, correlations between elements are on the right. 0.99 is the prior. This? This is something we'll have to come back to. If you do this, you'll probably get warning messages saying there's divergent transitions. We talked about the divergent transitions a little bit on the week on MCMC. It's basically saying Stan was taking too big of steps for this posterior distribution that was changing too rapidly at parts of the thing. So increasing adapt delta from its default value up to 0.99 basically tells Stan to have smaller steps. This, I now realize, is confusing because it involves the word delta. However, this is the lowercase Greek letter delta. And what I was talking about before is the uppercase delta, which is a variance. That delta is just a tuning parameter for Stan. It's not part of the prior.
What is the default?
In Stan, it's 0.8. In our Stan arm, it's usually higher, like 0.95 or 0.99 or something, just because we don't want people to see divergent transitions very much. But it actually came up in this case, so I had to bump it up from 0.95 to 0.99.
How it is in BERT? Like
In what?
BRM.
In BRM,
Yeah,
that's what we're going to learn next week.
like it's the same method?
No, I think they use 0.8 as the default. Okay, so we get the results. You know, here's the posterior mean, the posterior, for these things. These are for the betas. We see the same thing that we saw before for this part that's called error terms, even though that's more of a frequentist description. So how would we interpret these estimates for the betas? Like, you know, what's the probability of pulling the left or right lever, depending on what sort of a chimpanzee you are? Right. Don't interpret. Construct yourself a new data frame that has 4 rows, 1 for each type of chimpanzee there is. You also need, or you can do some other things here, but in this case, I specified that we're going to talk about group 1. So this is for the 4 different types of chimpanzees if they're in group 1. It would be different if they were in some other group because we have all these specific group-specific parameters. You can call posterior predict, but that's going to draw from the posterior predictive distribution. And so the result of that is going to be a bunch of zeros and ones, which is sort of, you can take the column means or whatever of that and they're consistent estimators for the probability. But it's sort of a noisy estimate. So what I've actually done here, and this really only works when your outcome is binary, I've called the posterior underscore linpred function, which gives me the posterior distribution of the linear predictor eta. I've also specified transform equal true, saying transform that posterior predictive distribution of the linear predictor to the posterior predictive distribution of the conditional mean or the probability. And I'm saying do it not for the old data set that I originally gave you, but for this sort of artificial data set that has the 4 types of chimps in group 1. And so with that, I get a 4,000 by 4 matrix that I can then summarize the probabilities of. And so this corresponds to a chimp with 0 condition and 0 post-social left. We get this posterior distribution of the conditional mean. For a chimp that is in condition 0 but is pro-social, I get this posterior distribution for the conditional mean for these 2 types of chimps if they're in group 1. And, you know, chimp number 3, it's, you know, more concentrated, shifted over to the left a little bit in condition 1 but not pro-social. The 4th one unfortunately got cut off, but there's only 4 columns. So you could summarize them numerically, you could summarize them with a plot, whatever. But this, all these numbers, they're between 0 and 1. They're probabilities. So we can interpret this not with like log odds and interaction terms that contributed log odds, but with probabilities, which is easier for people like, you know, zoologists or whatever who were studying these data to understand, and easier for you to understand. And we get full uncertainty because, you know, this is a 4,000 by 4 matrix, and we can, you know, use standard deviations or credible intervals, whatever, to, you know, quantify our uncertainty about these things. So there's really, you know, no reason why you should interpret some hard to interpret thing that even if you do it correctly, you're not going to be able to explain to, you know, a substantive researcher. So put it all in probabilities, or whatever is the sort of natural unit. So if probabilities are too hard for, you know, whoever you're talking about, you can say, you know, you expect 37 out of 100 chimps that are of type 1 to pull the lever. And if, you know, 37 is easier, 37 out of 100 is easier for somebody to understand than 0.37, fine. You will encounter people that way if you have not already. Okay, so almost out of time. Last thing I wanted to point you to is that on the CRAN webpage for RStanArm, there are, in addition to the documentation, a number of vignettes, approximately one for each of the fitting functions in RStanArm, inclusive of this one under hierarchical partial pooling, which is longer than the rest and goes into considerable detail about a very simple example with baseball data from 1975. You know, there was sort of data collected for this first month of the baseball season as to how many hits they got and how many at-bats. And then, you know, predicting the rest of their season based on that, and then comparing it to what actually happened in that. So it goes through, you know, the different sorts of models with partial pooling, which is the hierarchical model, versus complete pooling, which is the sort of model we learned about before spring break, versus no pooling, where you sort of estimate a separate model for each group. Goes into this idea of a posterior predictive distribution and how to do it correctly using RStanArm, how well it predicts new observations, doing LU, doing the posterior predictive checks. And so this is sort of a case study in all the things you can and should do with a, you know, Bayesian model, Bayesian output, even for a very simple data set and a very simple model where there's no like predictors. We're just letting the coefficient vary from one baseball player to the next. So if you want, or even if you don't want, you really should read through this carefully to get you know, firm grasp of like the whole process of specifying and interpreting and checking hierarchical model that you can then sort of apply when you estimate, you know, more complicated models on other things besides baseball. Okay, so I will see you on Tuesday. We'll start to learn the aforementioned BRMS package. This will require that you have a C++ compiler installed on your computer, which, as you know, history would suggest, is going to be a hit and miss process. So it's good to get started on that like tonight. I will send out a link on Piazza to the instructions for how to do that for each of the 3 major operating systems. So if you follow those instructions, it should be fine, but not everybody's going to be able to follow the instructions as written, in which case you'll get like a broken compiler. So let's start this early so we have as many opportunities to go through that process before Tuesday, when you're going to actually need the compiler to be installed and working. All right, see you then.
What was the compiler for?
Stan.
Is it